A billion stars. Just think about that for a second. Mapping a billion individual suns with, well, unbelievable precision.
Yeah, it sounds like something out of science fiction, doesn't it? But that was the real, incredible ambition behind the Gaia mission right from the very beginning.
And that's what we're diving into today, isn't it? We're looking back at the original scientific blueprint for Gaia, the case they made for it way back in 2000.
Exactly. We've got this fascinating document, thanks to one of you listeners, detailing that early scientific rationale.
Our mission for this deep dive, then, is to really unpack those initial scientific goals, the discoveries they were hoping to make.
And it's really interesting, maybe even a bit revealing, to look back now, knowing what Gaia has actually delivered over the last decade or so.
Okay, so the year 2000, this massive idea didn't just appear out of nowhere, I assume. It must have been brewing for a while.
Oh, absolutely not. By 2000, Gaia was already a serious candidate, a contender for one of ESA's big cornerstone missions. This was under the Horizon 2000 Plus program. And it wasn't a sudden thing at all. It came after years, literally years of intense preparation. There was a formal concept and technology study that ran from about 1997 to 2000.
A study just to see if it was even feasible.
Precisely. And it was thorough. It resulted in this huge report, nearly 400 pages long. The reference is ESSCI, basically pulling together all the thinking from a lot of people.
Wow, and it sounds like they assembled quite the team, a real brain trust, to figure out this scientific vision early on.
They did. They set up this pretty comprehensive advisory structure. At the very top, you had the Science Advisory Group, the SAG,
Yeah.
that was chaired by Michael Perryman,
Oh.
and it had 8 external scientists on it. They were chosen very carefully. You needed people covering the science goals, obviously, but also the technical side and, well, let's be honest, representing different European countries, too. That matters.
Politics and geography, sure. Can you name a few of those key people, the
Yeah.
ones really shaping the core ideas back then?
Yeah, sure. Let's see. The SAG members included K.S. de Boer from Bonn, Jerry Gilmore, Cambridge, Eric Hugg from Copenhagen, Mario Lattanzi from Torino,
Okay, big names.
Leonard Lindegren from Lund, Xavier Lurie from Barcelona, Francois Minard from Grasse, and Tim Dezieux from Leiden. A really strong group.
Definitely a powerhouse lineup.
Yeah,
And it wasn't just these external folks, right? ESA had its own internal team pushing this forward, too.
that's right. Inside ESA, people like Oscar Pace, Martin Heckler, Sergio Vellante, and Fabio Favaro were providing crucial support to the SAG. They also brought in expertise from 4 others in ESA's space science department, and crucially, the engineering side was heavily involved from the start.
That seems vital for something this complex.
Absolutely. There were 11 engineers from ESA's technical directorate involved, each bringing their own specialty things like the onboard computers dealing with radiation in space, thermal control, the structure itself, antennas, communications, keeping the spacecraft pointed correctly.
Attitude control, yeah.
The CCD detectors, which were fundamental, and even the system for monitoring the basic angle, which was key to the whole measurement concept. Super precise stuff.
So a massive collaboration. Science, engineering, internal, external. And then there were more groups under this main SAG.
Yep. 3 main working groups feeding into the SAG. You had the Science Working Group, co-chaired by Tim Dezieux and Jerry Gilmore, with about 18 scientists really drilling down into the science objectives.
Okay.
Then an Instrument Working Group, Leonard Lindegren chaired that one, with 16 people focused on, well, the instruments, how they'd work, what they could do.
Makes sense.
And finally, a Photometry Working Group, led by Fabio Favada, another 18 people, concentrating specifically on how Gaia would measure the brightness and colors of all those stars.
And that wasn't even everyone.
No. On top of all that, there were another 50 or so European scientists involved as members at large, kind of contributing expertise as needed. It was a huge community effort.
It really shows how much momentum was behind this idea. And you mentioned industry earlier. They were involved even at this stage.
Yes, definitely. ESA had already placed 2 significant industrial study contracts. One went to Matra Marconi Space. They were looking into using big, single-piece mirrors, monolithic mirrors.
A key technology choice.
A very key choice. The other contract was with Alenia, and they were exploring a different concept, using interferometry, like linking smaller telescopes together electronically.
So exploring options.
Exactly. That early industrial input was absolutely vital for figuring out the technical design and just what was actually buildable.
Okay, so with all this groundwork, all these people involved, what was the core scientific dream? What was the big picture goal back in 2000?
The absolute core. It was building this unprecedented 3D map of, well, around 1 billion stars in the Milky Way, and even looking out towards our nearest galactic neighbor.
Just knowing where they are.
Not just where they are, but crucially mapping their motions too, with
Yeah.
incredible accuracy. The idea is that how stars move today tells you about the past. It's like a fossil record.
Right. Tracing the galaxy's history.
Exactly. It gives you clues about how the Milky Way formed and how it's evolved over, billions of years. And the third piece was comprehensive photometry,
Measuring their light.
measuring their light very precisely in different colors. This lets you figure out their basic physical properties, things like how bright they truly are, their temperature, their surface gravity, even what elements they're made of, like decoding starlight.
So a full census position,
Mm.
motion, physical properties for 1 billion stars.
Yeah.
That still sounds utterly immense. What kind of technical capabilities do they think they'd need?
Well, they knew they had to measure the positions repeatedly over and over for a huge number of objects, right down to magnitude 20, which is pretty faint.
Okay.
The plan also included having the spacecraft itself be smart enough to spot things that change variable stars, supernovae exploding in other galaxies, maybe gravitational microlensing events, and definitely asteroids in our own solar system.
Onboard detection.
Yeah. And the accuracy target.
Mm.
Initially, it was just staggering. They were aiming for 10 microseconds for a star at magnitude 15.
10 microarcseconds. How
Uh-huh.
small is that, really?
It's almost impossible to visualize. The analogy they used was measuring the width of a human hair from 1,000 kilometers away.
Wow. Okay. That's precise. Did they actually achieve that?
They ended up descoping it slightly later on to around 25 microarcseconds at 15th magnitude, which is still phenomenally good, let's be clear. But yeah, that initial 10 microarcsecond goal shows the level of ambition.
Incredible. And what about distances and motions? How far out could they reach?
The goal was distance accuracy down to 10%. Even way out to the galactic center, that's about 30,000 light years away.
30,000 light years with 10% accuracy.
Yeah. And they even thought they could measure the tiny sideways motions of stars within the Andromeda Galaxy, our nearest big spiral neighbor.
Measuring motions in another galaxy. Okay, that's impressive. So, given these, well, revolutionary capabilities they were planning, what kind of science did they actually predict? What was the inconceivable harvest, as the document put it?
Huh. Yes, inconceivable harvest. I like that. Well, a huge one was finally nailing down the origin and history of our own Milky Way.
The big picture.
The big picture, using the oldest stars, looking at their chemistry, their motions, essentially reading the galaxy's formation history, testing all the different theories about how galaxies like ours assemble.
Like cosmic archaeology.
Exactly. And a key part of that was finding the leftover bits, the debris from smaller galaxies that the Milky Way swallowed over time, these tidal streams of stars. Gaia was expected to be brilliant at finding those.
Right, the shredded remnants. What else?
Dark matter, that was massive. We knew it was there, kind of, from how galaxies rotate. But Gaia promised to map its distribution across our galaxy by tracking the motions of millions, billions of stars, seeing how they're being pulled by gravity you can't see.
Using stars as test particles for the invisible stuff.
Precisely. It was about moving from theory to actually mapping the dark matter scaffold.
And what about understanding the stars themselves? Any breakthroughs expected there?
Oh, absolutely. They expect to build a much better census of really young stars, pre-main sequence stars, to understand those very early stages of stellar life.
Before they start burning hydrogen properly.
Right. And also catching stars in really rapid phases of evolution, phases that are short-lived and hard to find otherwise. The sheer number of stars and the precision, it was expected to just revolutionize our models of stellar structure, stellar evolution ages, for basically all types of stars.
So refining our understanding across the board.
Across the board. Plus, establishing a really rigorous distance scale. Not just estimations, but accurate geometric distances throughout the galaxy and even beyond into the local group.
The cosmic distance ladder.
Building a much stronger foundation for it, yes. And understanding star formation processes and the dynamics, the sort of chaotic dance of stars within our local galactic neighborhood.
It really sounds like they expected Gaia to touch almost every corner of galactic and stellar science. Were there specific types of objects they were hoping to find lots of?
Yes, the predictions for discovering new sort of exotic objects were pretty exciting too. The 2000 report talked about finding potentially thousands of exoplanets.
Nah, planets around other stars. It was still pretty early days for exoplanets back then.
It was, and not just finding them, but being able to measure their orbits and even their masses using the astrometric wobble method.
Okay, what else?
Tens of thousands of brown dwarfs, those failed stars, and also white dwarfs, the endpoints for stars like our sun.
Filling in the gaps in the stellar graveyard.
Kinda, yeah. And because Gaia scans the whole sky repeatedly, they predicted finding something like 100,000 supernovae exploding in distant galaxies.
Wow. How would they follow those up?
The plan was always for rapid alerts, so ground-based telescopes could swing into action and study them in detail as soon as Gaia spotted them brightening.
A synergy between space and ground.
Exactly. And closer to home, in our solar system, a huge boost was expected. Finding maybe tens of thousands of new asteroids, maybe finding some of those elusive inner Trojans near Earth's orbit, and definitely finding many more trans-Neptunian objects, things out beyond Neptune, like Plutinos.
So a solar system bonanza, too. It's just the sheer scale of it all. And it wasn't only about astronomy and astrophysics, was it? I think you mentioned fundamental physics tests.
That's right. This was a really fascinating aspect. Because Gaia's measurements were going to be so incredibly precise, it offered a unique way to test Einstein's theory of general relativity.
How so?
By measuring with exquisite accuracy how starlight bends when it passes near the sun, or even near Jupiter and the other major planets.
The gravitational lensing effect.
Exactly. Measuring that bending probes the structure of space-time itself. They hoped to see if it matched general relativity perfectly or if there were tiny deviations, maybe even signs of like a scalar component to gravity, not just the tensor form in standard GR.
Pushing the boundaries of Einstein's theory.
Potentially, yes. They also aimed to measure certain parameters, the ppn parameters, gamma and beta, which quantify possible deviations from GR, with much better precision than ever before.
Okay.
And also get a better handle on the sun's quadrupole moment, J2, which is basically how much the sun bulges at its equator due to its rotation.
Tiny effects, but measurable with Gaia.
That was the hope. And even more fundamental stuff like putting new limits on whether the gravitational constant big G is actually constant or if it changes very slowly over cosmic time.
Yeah.
And maybe constraints on low-frequency gravitational waves.
So Gaia wasn't just mapping the stars, it was using them to test the fundamental laws of physics. That's pretty profound.
It really is. It shows the breadth of the vision.
And the report also placed Gaia in the context of other science happening around 2000, didn't it? Why was it the right time?
Yes, they definitely highlighted the timeliness. We were making huge strides in understanding the very early universe from studying the cosmic microwave background think Planck, although that flew later, the groundwork was there.
Right, the universe's baby picture.
Exactly. And we were seeing further back in time, observing very distant galaxies with Hubble, and planning for even more powerful telescopes like, well, what became JWST, and the big ground-based ones like the VLT.
So we had the beginning and the distant past coming into focus.
We did, and theories of how structures like galaxies form were getting much more sophisticated, but there was this gap. To really test those big cosmological ideas, you needed a detailed, high-fidelity map of a typical galaxy right here, right now.
We needed to understand our own backyard to make sense of the wider universe.
Precisely. The Milky Way was the perfect laboratory. Gaia was designed to provide that crucial ground truth, that detailed local benchmark to connect the early universe observations with the theories of galaxy formation.
It bridges the gap. And it's interesting, you mentioned the target magnitude and accuracy earlier. They weren't just arbitrary numbers, were they? They were specifically chosen to observe certain things.
Absolutely. That ties into the concept they called galactic tracers by design. The limiting magnitude, around V20 or 21, and the astrometric accuracy goals were driven by the need to observe specific types of stars, stellar populations that act as reliable tracers.
Tracers of what?
Tracers of the galaxy's structure, its formation history, the distribution of dark matter. Different types of stars are good tracers for different things in different parts of the galaxy, like the halo, the disk, the bulge. You need to be able to see those specific stars clearly.
So the instrument design flowed directly from the key science questions.
Very much so. It was incredibly well thought out.
It really demonstrates the depth of planning. And it's quite telling that even in this incredibly ambitious 2000 proposal, they were already thinking about what Gaia couldn't do, looking beyond Gaia, even then.
Yes, that's a mark of good scientific planning, isn't it? Acknowledging the limitations. The report did include a section on science questions that would likely remain tough even for Gaia.
Like what, for instance?
Things like resolving individual stars in the super dense cores of globular clusters, or seeing right into the galactic center through all the dust and gas. Also, mapping really fine scale bumps and wiggles in the Milky Way's gravitational field, and maybe even doing cosmology by measuring the sideways motion of really distant galaxies or quasars directly. That's incredibly challenging.
So even as they were launching this revolutionary mission concept, they had their eyes on the next set of challenges. It's just quite inspiring looking back at the sheer ambition and detail of that original Gaia science case.
It really is remarkable. And, the most satisfying part is seeing how much of that vision, how many of those predictions from over 2 decades ago have actually been realized or are being realized right now thanks to the missions data.
It just gives you a huge appreciation for the foresight, the planning, the sheer intellectual effort from all those scientists and engineers involved back then. It wasn't just wishful thinking. It was a carefully constructed roadmap for discovery.
Absolutely. And maybe it leaves us and you listening with a thought to chew on. What are the Gaias of tomorrow? What missions are being planned now, perhaps just as concept studies that will completely revolutionize our understanding of the universe 20 or 30 years down the line, building on what Gaia has taught us?
That's definitely something to think about. What's the next impossible dream?